Okay, so we're going to be talking about Unit 4 today. Unit 4, which is Section 4.1, which is all about the roots of real numbers and radical expressions. Specifically, this will take place over a subsection, so it'll be 4.1.1 and 4.1.2. We're doing point 1 today, point 2 tomorrow, okay? So, when we define a perfect square, as we did in our warm-up, we are given two examples, right? Or at least I'm going to define a perfect square in two examples here. A perfect square is the product of a number multiplied by itself. Right? So example, you have 64 is a perfect square because B/C, 8 times 8 is 64. Another one would be 25 is a perfect square because 5 times 5 is 25. Right? Pretty simple stuff. Now, the question, though, is that you've done perfect squares. What exactly is a square root? Like, what does it actually mean, right? How do you find the square root of a perfect square? So the thing is, a square root of a number is the value that when multiplied by itself gives the number. All right? To find a square root, you look for the number that multiplies by itself to equal that number. Okay, now, however, much like in our warm-up, there are some times where perfect squares do exist and don't exist, and we have to take the square root of them. So we have to approximate the following to the nearest tenth. Now, nearest tenth is just personal choice. Okay, 9 times out of 10, they won't tell you what to round to, and usually you always assume the 10th place. However, in my class, as I've told you before, always assume the 3 seg figs, i.e., the tenth, thousandths, millionths place. Right? So 0.001 is the one I'm talking about. That's the one I want. Okay? So let's take a look at an example right here. Always ask yourself, which two perfect squares is this number between? So let's take a look at 45. Okay? 45 is between what two numbers? Okay? Well, we know for a fact that the square root of 36 is less than 45, and the square root of 49 is bigger than the square root of 45. So we know it's got to be between those two numbers. Now, you could go about that way, right? And then you got to do some guessing check stuff, and it's a complete mess, and bleh, no. Or all you have to do is split the number between 5 and 9. Then you split 9 into 3 and 3. Now, please pay attention. We're looking, now there's an understood 2 right here, okay? He's a ghost, but he's understood, much like how we have, x first power to this, we just write this as x, right? Same principle. We don't need to add all the extra fluff around it. We know what it's doing. So we know that the square root has the square of 2, which means we're looking for partners of 2, or pairs. Right here are 2 3s. That means they're going out for a date. 5 is all by himself. He's going back inside the house. Okay? That's what's going on. Okay? Now, when they go out, they only have 1, meaning that when 3 and 3 are paired, there's only 1 3 that's going to come out here. So 1 number per pair. Okay? 1 number per pair. That means that we're going to get 3 radical 5. Or, if you would like the decimal answer, if you plug in the calculator, 6.7. All right. Now, when you get to this point, so you go in the decimal, 9 times out of 10, they will ask you for this answer. Very rarely do they ask for the decimal answer. Okay? That is crucial. So this is what we call the radical form. Okay? We'll learn more about the word radical later on, but this essentially is the simplified radical form. And this is what I expect to see all the time. I don't want to see decimals. Now, if you put a decimal answer, it's fine, but it's not as accurate because you're kind of saying, well, the square root of 5 is 0.7 something, 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 something. And that's not very accurate. But when you just say radical 5, we know, okay, we have a leftover square of 5, a complete square of 3, we're good. That's what that's basically saying. No different than you'll learn next year something called about completing the square. That principle comes back to this as well. The two are somewhat related, not like computationally, but in terms of conceptually. All right, now let's take a look at another example real quick. Okay, so let's say I have the square root of 72. Again, we're going to split 72 into its multiples, 8 and 9. 8 splits into 2 and 4, which then splits into 2 and 2. I'm done. Once you get to where there's all prime numbers, you have to stop. You can't split prime numbers into 2 and 1. You'll just get an infinite feedback loop. Okay? We do 9, we get 3 and 3. So now we have dance partners here, dance partners here. So it's a double date. Great. So that means that these are both going outside the house. I cannot draw arrows sometimes to save my life. Okay? And that means that 2 is all by him lonesome. He doesn't have a prom date. He just stays home. Okay? Now, what that means is that you're going to get, as I stated up here, 1 per pair, which means that I'm going to write out here 3 times 2. The numbers you take out in those pairs, you multiply by each other in front of the radical, similar to how coefficients work. The radical, if you mentally replace it with x, follows the same rules now. He's just along for the ride. He's not affecting those two guys. So then the answer would be 6 radical 2. And there's your answer. So the square root of 72 is 6 radical 2, which again makes sense because if I were to simplify that back, 6 squared is 36, right? Oh, no, that doesn't work. Sorry. You have to split it first. So if you were to simplify it back, if you were to square that entire thing, you should end up getting 72, which you do because square of 6 is 36, and square root of a square is just what we call the radicand. We'll learn about that again later on. Radicand referring to the 2 on the inside. Okay. And so therefore it's 2 times 36, which indeed equals 72. We're happy. Okay. So that's how you do the simplification of radicand.